This is the second installment of writing, interpreting, and using a linear model. For our next example, we can see that we already have the graph of the equation, and they were already nice enough to write the model, the mathematical model for us. So now we're just going to be answering questions based on that information. So first, we're determining the slope, and then we're going to interpret that in the terms of the question. So make sure that you've read the information above. But the slope should be fairly easy to find because we know that the slope is always being multiplied by x. So my slope would be 0.14, and I'm going to interpret what that means in the context of the question, and that means for each additional year, and we could even put past 1970, because as you can see, 0 means every year, or 0 means 1970. So for each additional year past 1970, what's going to increase? The minimum wage increases, or increased, by 14 cents. That would be our slope of the equation. Next, we're going to find the y-intercept, and we're going to interpret that. So again, we already have this written. So our y-intercept, our b value, is 1.60. The interpretation of that would be in the year 1970, and again, it's 1970 because that's at year 0, and they tell us year 0 represents 1970. The minimum wage was $1.60, 1.60. Now we're going to use that equation to approximate the minimum wage in 1985. So again, I'm going to use the function that they've given me, and I'm going to replace the x value with the value that would represent 1985. So down here, 0 equals 1970, which means the year 1985, I wouldn't put in 1985. It would be 15 years past this, so I'm going to put a 15 right here. When I multiply 0.14 times 15, I get 2.1. I'm going to add that to 160, so that's going to give me 3.7. And again, I'm using that to approximate the minimum wage. So even though my answer is 3.7, I would say the minimum wage in 1985 is $3.70. Our last example also has several parts, so this is sort of putting it all together. Now we've got a function here. We don't know the equation this time, but they're asking us to use these 2 points that they have plotted for us to find the equation. So now we're going to go through that full process where we're first going to find the slope, y2 minus y1 over x2 minus x1. When I subtract, I get 2.9 divided by 10. Now typically we would want to leave our slope as a fraction, but quite often when we're dealing with linear modeling, we go ahead and just turn that into a decimal. So if I took 2.9 divided by 10, that's 0.29. Now I'm going to use my point slope form. So y minus my y value, I'm choosing that second point, equals my slope, my slope, and then x minus my x value. I'll distribute the 0.29, and that gives me 7.25. I'll add to each side to get y equals 0.29x plus 12.45. So this is now the equation that I will use to predict. So this equation doesn't change. I often have students who try to change this equation or use point slope form again, but this is the equation that I'm going to use moving forward. So anytime they ask me to interpret something or predict something, this is the equation I'm referring to. The next part says determine the slope of the line and interpret what it means. And so again, if you'll remember, I had 0.29x plus 12.45. So that slope would be 0.29. So my slope would be for every additional year, or for each additional year, and I could say past 1980 if I wanted, the number of women graduating from law school, I'm going to shorthand this a little bit, the number of women graduating from law school and I'm not going to put is 0.29 and then that number is in thousands. I'm going to go ahead and take 0.29 times 1,000 because I want to know exactly how many women that is. So if I multiply that, I get 290. So the number of women graduating from law school increases by 290 women. That is how I would interpret my slope. Again, I didn't use the 0.29 because it wouldn't make sense since that number is in thousands, so I took that times 1,000 to find the actual value, which is really just me moving it 3 decimal places. Now they're asking me to use this to predict the number of women who will graduate from law school in the year 2015. Again, I'm going to use my equation, and instead of x, I'm going to put in the value that would mean 2015, which is 35 years past 1980. And then this was 12.45. When I multiply, I get 10.15 plus 12.45. When I add those together, I get 22.6. And again, if I am now trying to use that to predict the number of women graduating from law school, instead of saying 22.6 and that number is in thousands, again, I'm going to take 22.6 times 1,000, which I would move my decimal 3 places, which would give me this value. So 22,600 women. And again, I would write that as a sentence. Would it be practical to use a linear model to predict the number of women who would graduate in the year 2050? Well, let's take a look at the values that they give us. Notice up to here, this would be, just like on our last example, this would be the year 2015. If I were to go all the way out to the year 2050, that's quite a ways away. That's an additional 35 years beyond the data that I have graphed. This is called extrapolation, when you are trying to predict something outside of the range of your model. And so no, we wouldn't, because extrapolation is very, very dangerous, because there are a number of things that will influence the number of women who graduate from law school. And those figures could either make that value increase or make that value decrease. And so no, we wouldn't, because it's extrapolation, which means we're looking at values outside of the range of values that we're comfortable with.